Okay, so this is lab 2 and we'll go through association rules, how to implement association rules through R. So I'm in Sakai and I will click lab 2, which is right over here, and it opens in web browser. So let's do the same thing that we did in lab 1, go step by step. Now, once again, hash sign implies that this particular line or row is a comment. It's not to be executed, just meant to tell you and tell R that, we're doing something over here. R will not execute these lines as statements. So with that, all these things, all these rows over here, they're just comments. I just want to say something about what I'm about to do in the next step. So here I'm saying lab 2 from data mining IFS 494 fall 2015. Download the file grocery.csv from Sakai and save them in a folder RLAB02. I'll refer your location as your directory. Okay, so the first thing that we have to do is we have to download this file called groceries.csv. So let's go to our Sakai resource folder and download grocery.csv. It's right over here. And once you download, open it in Excel. Excel opens CSV by default. CSV stands for comma separated value. So even though in Excel you may not see the separator, but the separator in this case is comma. So be cognizant of that fact. This file is delimited by, separated by comma. That's what CSV stands for. Okay, so this is how the file looks like. Every row is a transaction, and this the length of the row defines how many items were bought. So in the first row means first transaction, 4 items were bought: citrus fruit, semi-finished bread, margarine, ready soup. In the second one, 3 things were bought. So the second is another transaction. Third one is another transaction where only 1 thing was bought, that was whole food. And the fourth one, again, 4 things were bought. So in total, we'll see later on, in total there are about 169 items in this data set. So this row can be as wide as 169 items. So there could be somebody who's buying all the stuff that is there in the grocery. That's possible theoretically. So it could be as wide as 169 items. It could be as small as only 1 item, as we saw in the row 3. So this is how the data looks like. However, the issue that we have with this data is that we cannot do a lot of things with this data. So for example, I want to find out how many citrus fruits were bought across the entire data set. Now I cannot calculate that very easily in this format. So what I have to do is I have to change this format in a way where I could do those kind of counts. And one of the ways of doing that is if I say copy the first transaction and I paste it over here and I call it transaction ID 1. So that's a transaction identifier. So this is the first transaction. And now what I'll do is I'll change the direction of this data. So there are 4 items in the first transaction. So first one will be the citrus fruit. The second one going to be the semi-finished bread. Then third one will be margarine. And the fourth one going to be ready soup. Okay, so this is the format that I want my data to be in, not this way. This is how the data is coming from the data warehouse team or whosoever is giving you the data. Maybe you're buying it from AC Nielsen. So, but I want the data to be in this format. And now I can easily calculate, okay, citrus fruit, in case there was one more citrus fruit, I can easily say, okay, there are 2 citrus fruit, 1 semi-finished bread, 1 margarine, 1 ready soup. So now things become so much easier. Here, if I have 169 items being bought in one transaction, that row will be 169 columns wide. That restriction is not here. So if in case I have a transaction that is 169 items in it, all I'm going to have is 169 rows. Not 169 columns, but 169 rows. So this table will keep growing vertically, and that's the reason whenever I refer to this kind of format, I call it vertical. So let's go back to our script and what we are trying to do in the lab. So I download the grocery.csv file. I looked at the file format. It seems like it's very horizontal. I'll have to make it vertical in order to make it useful. Thereafter, what I have to do is I have to create a table, an empty table in the database. That is what this particular command is doing. Now, the good thing is you do not have to execute this command. I've already created a table called grocery in the database for you, so you do not have to execute. And the reason why I'm showing this is that if you take this script to your workplace or maybe your future job, and you're wondering, how the data actually ended up in the database, so this is a way to do that. So the first thing I'm going to do is I'll create an empty table. It's a staging table, and this table is named grocery, as the name itself suggests. Grocery, and the syntax is create table and the table name, which is grocery. It will have only one column called line, and the data type of this column will be text. So that is what this particular statement is doing. Now with this statement, once I execute this in Postgres database, it will create an empty table. There is no data in there. So I have to put the data in there from a flat file. So for that, I execute this statement. Again, you do not have to execute this statement because I've already done that for you. And with this data, copy grocery. So copy grocery table from this particular CSV file, which is sitting on the D drive of the server, not your laptop, but server. So I've already taken care of this step as well. You do not have to do this. So copy grocery from D data RLAB02 grocery.csv. It will copy all the data that is there in the CSV file, put into grocery table. And after that, grocery table is populated. However, at this point in time, still we have the same problem. Of course, the data is in database, but still it is in very horizontal format. I want to make it vertical format. So for that, I'll have to do some transformation. I will have to use some analytical functions, and I'll give an example of an analytical function which is very useful in this context. So before we get into that, let's start our SQL interface. So I click hide SQL over here, and it opens up a window. In the first network type, choose Postgres Experimental. Do not choose MySQL, which comes by default. In a host name, put 147.126.64.66. In the username, put data miner 1, 2, 3, 4, whatever the number I assigned to you. The password will be fall 2015. Port is 8432, and the database will be INFS 494. Now, be cognizant of the fact it's case sensitive. So uppercase INFS 494 will not work. So make sure all these things are populated the way they are supposed to be, and then hit open. And this will open the browser where you can see all the tables. So now there are a bunch of PG temp or PG catalog or information schema. You do not have to do anything with that. All you have to do is double click this public over here. That's where the tables are residing. And there's one table called grocery, which has 1.6 MB data in it. And if you want to look at that, if you click it, it will open the definition of that table. So you can see that there is only one column called line, and it is of data type text. So far so good. We can also look at the data because I've already executed the statement to populate this table. The data looks like this, very much like the CSV file, because we just read the CSV file, wouldn't do any kind of transformation. Now, the next step is to transform this data into the format that we just talked about in the Excel sheet. So right now the data is in this format in the database. I want to make it look like this. How to do that? So for that, let's go to our script. So here I do something called create view. Now view is a virtual table, it's not a real table. In case you have a SQL query that you're running all the time and you do not want to type all the entire query, which could be maybe 2 pages long, again and again, what you can do is you can create a view, which is a virtual table which encapsulates this entire SQL query. And whenever you call this view, which appears like a table, this particular query is executed. So that is what I'm doing over here. Now to understand the syntax, this query, the first thing is that I'm executing an inner query. And what this inner query is doing is it's creating a transaction identifier because my original data doesn't have a transaction identifier. I need a way by which I could say, okay, this transaction is different from other transaction. So for that, I use an analytical SQL function, a row underscore number, parentheses open, parentheses close. That's the syntax for that. And what it does is it generates this serial number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if there are 9,835 rows, uh, it will generate number from 1 to 9,835, one for each row. Over parentheses open, parentheses close. That implies over the entire table. I'm not partitioning this table into a bunch of subset of the data. I want it across the entire table, 9,835 rows. And I will call that serial number TID. So that's what this as TID means. And then I will also need the line, which has all that information about all the items which are bought in that transaction from grocery table. Now, with this uh, statement, this query, what it has done is, so my data is very much like this right now in the database. What this query does is it creates a new column called TID. So this is the TID which is created by that row underscore number parentheses open parentheses closed, and all it's doing is it's doing this thing, creating a rolling serial number going back to the last row, which is like 9,835. So that is all that subquery is doing. So after that subquery, this is how the data looks like. This is how the data looks like, and and that subquery is sitting over here. Now I will read out of the subquery in my next SQL statement, which is the outer query. In outer query, I'm saying is select TID, which is this TID, select TID, and then another function called regexp, that stands for regular expression underscore split to table. Line is this whole thing. So this is line. So split this line by comma, and whenever you find a comma, create a new row. So it will read citrus fruit, then it will find a comma because of CSV. Remember that? It's a comma separated value. So after citrus fruit, it will find a comma. It'll put semi-finished bread into the next row. Then we'll find a comma, it will put margarine into the next row. Then find a comma, it will put ready soup into the next row. And thereafter, our data gonna look very much like this. So this is how we want the data, and that's exactly what this particular expression is doing. Regular expression underscore split to underscore table, parentheses open, parentheses close. In the middle, you're saying take line, split this line into multiple rows based on where the comma is. So that's exactly what this function is doing. And put this query into a view called grocery underscore vertical. So after this, whenever I call grocery underscore vertical, my data gonna appear in this format. So let's see how our data looks in grocery underscore vertical. So let's go to query tab and type select star from grocery underscore vertical and say limit 10. So that's a way, give me 10 rows only. So this will give me 10 rows. I can even make it 100 just to see like more data in there. And just hit this one and we'll execute the query. So now I see the top 100 rows, and I can see, okay, the first transaction had 4 items, so 4 rows have been created. Second transaction had 3 items, 3 rows have been created. The third transaction only had 1 item, so only 1 row. And then fourth transaction had 4 items, so 4 rows. Fifth has only 4, so 4 rows are there. And then 6 has 1, 2, 3, 4, 5. 5 rows have been created. So this is how the grocery underscore vertical appears. It's not a table, it's a view. It's reading from grocery table that we uploaded from CSV file, and it transforms the data in this format. So the beauty of this thing is I can do a bunch of things with this. I can do count star, um, and then read exp, hard to type, and that's the reason why we're going to change the name in R. We'll see that in a minute. Um, so count star, which will give us the number of rows. So that's what count star means, number of rows. Group by 2. 2 means this. So group by 2, and I want to order. So this is 1, this is 2. So group by 2, that means group by regular expression underscore split to table. And then order by 1, which is count star. So count star is 1, rejects split to table is 2. So group by 2, order by 1, and I want it to be descending. So once I do that, it will execute, and I see that very rapidly the 2513 is the most frequent item, and very rapidly the whole thing uh, decays, and I can, instead of looking at all the 169, I can just look at some of the top 20, 30 items, and that describes the whole thing. And that's what a priori algorithm is all about. If you recall, we are only interested in those items which are frequent. So this is a way by which I can look at the distribution of data, and I can see whether there's a decay in the frequencies, which mirrors a little bit like Zipf distribution. So once I look at it, it's not exactly Zipf distribution, but it's kind of Zipf distribution. It doesn't have to be exact identical, but the point is, can a priori algorithm utilize the distribution of the data to cut the data set, to make it not that big an algorithm, not that much of a cost. And it looks like it's a good candidate. It's not an ideal candidate, but good enough. And if I had the data in this format, it was simply impossible to run this kind of query. So that is the reason why I had to convert the data in this format, because now I can do a lot of count stars, which otherwise was simply impossible. Okay, so let's go to the next step. So we have created the view, everything is fine. Let's do the same thing that we have done in lab 1, create a working directory. So set a working directory. For that, we'll call RStudio, and it opens RStudio. Okay. Now, one of the questions that people had in the class was that, when I open the RStudio, I do not see 4 windows, I only see 3 windows. Well, if you go over here and you say, okay, new file, RScript, it will open another window. So this window is for the script. So if you do not have any script open, you will not see this window. Once you have a script, you'll see this window. So it's not a big deal. But this is where we type all our stuff, all our commands. So I'll do set wd, and then again I will go to my desktop and I'll create one folder, and I'll call it lab2. Okay, so I've created this folder. Go to the properties and copy this whole location, and then come over here, and then of course RLAB02, and do not forget to change the direction of these slashes, otherwise it's not going to work. Okay. Okay, now it should be fine. So this is our working directory. Let's check. Uh, this is a working directory. Do list.files. Shouldn't be anything in there because it's an empty directory. I just created it. So there's nothing in there. But this is all we covered in lab 1. Okay, so let's go back to our script. Now what we have to do is we have to create a connection with the database, because all our data is sitting in the database. R doesn't have any of the data. R is a statistical tool. It's not a database. Data resides in the database. Okay, so for that we have to call R PostgreSQL, and for that I have to give this command called library R PostgreSQL. However, if you recall our lab 1, before you call the library, that particular package has to be installed. So before calling the library, I will do install.packages, which I've already covered in lab 1, R Postgres. Now be cognizant of the fact that it's case sensitive. So if you make any mistakes in the spelling in terms of cases, then R will complain that there is no package called R PostgreSQL, although it's a very popular package. Okay, so now once I hit enter, it will go out there, look in the internet where our PostgreSQL server is, SQL package is. It will download all the stuff. So it has downloaded, it checked the package, everything is fine, and so we have the package. Now let's call load the function. So library and R post, and here it is. Okay, just hit enter, loading DBI package. So now our PostgreSQL is loaded. Now, in order to connect to the database, excuse me, you have to make a connection. So this is the command to make the connection. I think we covered that in our first lab, but let me repeat that once again. So the function I'm calling out of our PostgreSQL is dbconnect. Again, be cognizant of this of the cases. If you put C to be lowercase, it's not going to work. Then which particular database I'm connecting to? It's PostgreSQL. Once again, case sensitive. It's surrounded by double quotes. Anything that is string will be surrounded by double quotes, comma. Which database you are connecting. So DB name is equal to INFS494. Again, case sensitive, double quotes around, comma, host, which server that database is running on. Host is equal to 147.126.64.66. The IP address of the machine on which Postgres server is running. Again, quotes are there, comma. Port on which the database is listening is 8432, or server is listening is 8432. There is no code in here because it's numeric, comma. Which user you're connecting as. So data miner 1, again, quotes are there, comma, password is fall 2015, the quotes are there, and then parentheses closed. And once you do that, connection established with Loyola server. Okay, so this is all fine. Now with connection, uh, we still haven't done anything. All we have done is we have created a channel through which we can talk to the database from our laptop. That's all we have done. Now, based on that channel, now we'll do the talking and we'll get a query executed, its result being put into a variable. So how to do that? So for that, the syntax is this one. So here what I'm doing is I'm calling a function from our PostgreSQL package. It's called db get query. Once again, be cognizant of the fact that Q and G are capital. If you make them lowercase, it's not going to work. Now this function asks which particular connection, which channel you're talking about, because that channel in itself has all the information about the database, about the server, about the port, about the IP address, about the user and the password. So this CONN has all that information. So we say, okay, CONN is a channel that I'm talking on, comma, and this is the SQL statement that I want to parse. I want to send it to the database, and once you get the result, you put the output of that SQL statement in this variable called gr. So let's hit enter, and now it is going to the database and getting all the things which are in grocery underscore vertical and putting into gr. Now if you go back to lab one thing that I talked about is that whenever you're making a variable out of database connection or reading a file, it will be of class data frame. So if you want to check that gr, it'll be a data frame. So that is good. Now if you want to see the structure, here is the TID, 111222, and there are only two columns. The other column is regular expression underscore split to table. It's of character and TID is of number. We all know that. In total, there are 43,367 observations. Um, that doesn't imply that we have 43,367 transactions. What that implies is that we have 43,367 instances of item being sold across 9,835 transactions. So we'll see that number once again. But this is to confirm that we read all the data fine. There are two columns in our data set, TID and regular expression split to table. Now, so far so good. But one thing that we realize, it's so hard to write this thing down again and again and again, and it's so hard to speak at the same time. So could I make this thing simpler? Could I rename uh, these column names? And the answer is yes, you can do that. And that's what the next step is all about. So next step, what I do is I execute this statement called column name of gr. And all it's saying is that column name of gr, which is a data frame over here, is the first column going to be TID and the next column going to be items. So change the column names of GR to be TID, the first column, and item to be the second column. And let's hit enter, and let's do the same thing that we did previously. If you do strgr, now you see that, of course, the first column name TID is unchanged, but the second one has become item instead of regular expression underscore split to underscore to table. So now things are so much easier to type and to talk, speak. Okay, so now, okay, my data is there, everything looks great, and you can do all those things that we talked about in the lab one, like head, just to see like how the data looks like. So this is the top 6 rows. You can do the tail of bottom 6 rows. You can see, okay, how the data looks like. It seems like everything is fine, and you can see over here the because this is the bottom 6 rows. In total, we have 9,835 transactions. Okay, so that is all fine. Now I will run a priority algorithm out of R. So for that, I'll have to call a package called arules. So in order to load that package, I have to issue command library arules. However, in this case, I already have installed arules. I do not have to do it. But if you're doing it for the first time, what you have to do is you have to issue this command called install packages and arules, and it will go out there um, and and install the package. Now, since I've already, called the library of A rules, I was already in A rules, and if I try to install that package, it'll restart my R session. That's exactly what happened. So it's going out there on the internet and downloading A rules .zip. Everything is fine. Let me see if I still have my GR is there. Okay, so GR is there, and I can do str on gr, and everything is fine. So okay, so I installed a rules package by issuing this particular command. Look at lab1. We do it multiple times over there, and be cognizant of the fact that when you install the packages, you have these double quotes around, which you do not need for library. Okay, so now package is installed. Let's load the function. So load that package. So a rules, and now the package is loaded.